For this final calculus challenge, let's try to solve this integral. Integral from 0 to 1 of 2 dx. Well, I think we can find out that it would be 2x, and this is going from 0 to 1. And that's just going to be 2, and you're going to plug in the 1, and then you're going to take another 2 and plug in your 0. So what we need to notice here is that this is the antiderivative of that. This is the derivative of that. It's really important for the next step. Well, let's take this to the next level, and let's say we want to integrate a couple of points, like 0, 0 to 1, 1. And this time I'm just going to put the derivative right there. So that's the derivative, that's going to be the derivative, and then I'm going to dot this with dr. So in this case, I just went in one direction, the x direction, but here dr is going to be more like dx, dy, dz, some combination there. And usually I'd have to parameterize this. And that means just transforming these stuff into terms of dt. So we'll do that a little later. But this, if that was the derivative, all I want is the antiderivative, right? So I'm just going to put the antiderivative as f, the regular function, and then we're just going to plug in the points. So 1, 1, and then subtract 0, 0, 0. And so this is how you would take that stuff to the next level. Let's apply this to the real world now. We're going to try one of the easier ones. It's going to be called a scalar line integral. Now this is good for calculating, say you had a wire, density of the wire. So essentially it would look something like this. You're going to have the function, and you're going to integrate the function over some length dr. And there isn't going to be a dot product there because there's no vectors. So here we're just going to take a to b, and we're going to have, like, say, the density function. But in this case, we're going to start looking at parameterizing things, because this might be a curved line. If it was a straight line, it would just be dx. You'd use that thing. But let's go ahead and parameterize this in terms of t, and then we're going to throw in the acceleration magnitude right there, and then there's the dt. So you have to parameterize this in order for this to work. Now, let's discuss with the r prime of t thing is in just a second. Well, what is this parameterization of dt's and things? Well, let's say we had a very kind of a straight line here. It might be a sloped line, but it would have to be straight. And then we're going to use this situation. Let's say we had like x naught and y naught over on this side. It's just 2 points. It could be in 3D space too, but let's put it over here as x comma y. And then at this point we'd say time equals 0, and at this point we'd say time equals 1. So now we've got this t's involved. Well, if we were to define some kind of an RT, we would say that RT is equal to 1 minus t, and then times the point A, which I'll call this point A and that point B, but we got x naught and then y naught, and those are certainly going to be in coordinates right here. So this is a very coordinate system. And then you're going to add t and then times x comma y. Okay, so you're taking the first point and you're adding the second point with this stuff happening. So you're parameterizing this. So if you were trying to solve this r of t thing, you would end up with some kind of vector. And that vector is going to be x of t comma y of t. So that's literally going to be your x, and that's going to be your y. Those are the 2 points that you could plug in back into your function. Let's say you wanted to take that magnitude right there. You would just basically have to take the derivative of that, and then you take the magnitude. So you do the square root of x prime of t squared plus y prime of t squared. And that just comes from there. Okay, the derivative of those two things. Well, let's say it wasn't just straight line like that, but it was more curved and twisted. So you could start from this point over here, x naught, y naught, and then you'd make your way over to this other point over here, which you could call x and then y. And it might be easier in this case if they gave you a y function, and you could just set that equal to f of x, y equals f of x. And then you would set x equal to just plain old t, and then you could set your t values equal to x naught going all the way to xf. And that would come from this, so x naught to xf over there. Now this dr thing over here, that would just represent that you're integrating over a line. The dA, that would represent integrating over an area. If you had a ds, capital S right there, then that would be integrating over a surface area, and that would quite literally equal fx squared plus fy squared plus 1, and then you'd also have to multiply that again by a dA over here, and this would be more like a warped area. Now there's a special surface area we don't have to use this formula for. That would be the surface of a sphere. You can actually just say, this is for a sphere, because it's a perfect, we already parameterized that as far as the area. The area of the sphere is the surface area of the sphere. So you can just use that equation. This would be p squared, and then sine of the phi, and then dp, d phi, and then d theta. Crazy. Now hopefully remember what a vector field was. It's essentially just going to be a field that has like 3 different functions. We would have a function A, a function B, and a function C that you could sort of stick into this XYZ thing. So any point that you try to plug in there, you'll get this vector pointing some direction. We've already covered this in a different video where we take a look at where the arrows point in a field. But let's try to imagine what this would mean if I took an integral of some function and I put that over and did some dr situation, kind of like what we did over there. Well, if you had your field pointing this direction, and this just comes from plugging points into there, and then you were going to integrate this direction across an r, notice the arrows are pointing this direction, and you're just adding up all those arrows. Now maybe they're not quite exactly straight, but you're going to add up, that component, how we take the components and stuff, right? So this would be positive if we were to try to add up all those arrows. But if we went the other direction like this, then naturally that would be negative, because this is the direction of integration and all the arrows are pointing backwards, so you're just adding up a whole bunch of negative numbers. So it's relatively easy. So the scalar line integrals were pretty easy because they're just regular functions. But if we were going to do vector line integrals, then we can actually start to calculate more interesting things. Like, for example, instead of density in this case, we can use one to calculate work. So we're going to try to calculate work with this integral. It would be integral of f dotted with dr. And that, if you were to try to calculate that, you should parameterize it. So you would use a to b here, those are just going to be the points, f, and then this is going to be xt, yt. We've sort of already done this, but you're going to dot this with the regular old r prime of t there instead of this magnitude. So this time you don't have to do any magnitudes. Now you might see this written in another way. It might be written like this: a dx plus b dy. And yeah, that would definitely be, you got to sort of recognize that those things are going to be written in those ways. There's a couple different ways to recognize it. This is how you compute it, though. And let's just make a note that dr is equal to x prime of t, and then y prime of t. And again, that just comes from over here. We're just making sure we remember that. Well, this one was a pretty easy integral because it was essentially in 2 dimensions. If this is x and y, you can integrate along the x and you'll just have to deal with the y components, right? But in the next integral, the flux integral, this one might be a little bit more interesting because we have to integrate this function and we have to dot that with the normal. And so the normal is going to point in some weird direction, right? Because maybe we're in x here, but the normal would be pointing in the z direction. And so it's going to sort of add this component to it, and we have to deal with that. sometimes. Now in the 2D planes, of course, it's going to be easy because that z component is just going to be 1. But if it wasn't, then we would sort of be using something like this. A, B, and then we have F. Again, we're going to parameterize this in t's, yt, and then we're going to dot that with this little normal dt. And the little normal is going to be equal to y prime of t and then negative x prime of t. Again, this is for the 2D situation, so we've got to sort of remember that. But we could rewrite this another situation, in another way. It would be negative b dx plus a dy. And this is just to sort of be able to recognize these things, what we're doing and where they're appearing in the math. Well, let's say it wasn't just an easy 2D situation, you had to actually calculate the normal. Well, if we were to try to do that, let's just remember that if it's along a line, then the regular n is equal to y prime of t and then negative x prime of t. And this is not normalized. So notice that this is with a unit vector on top. So you need to actually take that and then figure out the magnitude of that, and then you have to sort of dot it and all that stuff. But this has already been done for you. It's going to cancel out with something else. So you don't have to worry about it in a two-dimensional situation. Just go ahead and use that. But if you have to go through a whole process and prove it, just know that that's actually just a regular n. Anyway, so the next one is going to be for a surface. And the surface is, let's say you want to make sure that you want to put your surface in this form, x, y, and z equal to 0. So once you have that, then you can figure out what the normal for the surface is. That's just going to be equal to fx, fy, fz. Let's say you didn't really have that much information and you kind of had to calculate the normal by hand. The normal is t divided by the magnitude of t, that's the tangent. The tangent is going to be equal to r prime of t. So if you actually know r prime of t, you can work your way all the way backwards, take the magnitude of the tangent, take the magnitude of the normal, and then find that and plug it all in, and just be a little complicated, but hopefully the shortcuts will work. Let's continue in 2D. This is where we find Green's theorem. Green's theorem. And this one is going to be for circulation. That word didn't really make too much sense to me at first, but remember these arrows that we're saying here? If we were to try to calculate work in a circle, then that would essentially be what circulation is, just calculating work in a circle. So it's kind of weird. But let's make a note of this symbol. This little symbol is a counterclockwise line integral, all the way closing itself. It's kind of as if you went a little circle right there. So we're going to say that if we close that line, we made an actual circle instead of just a straight line, but a full circle, then we're going to go f dotted with dr, and we're going to try to recognize this form. A dx plus b dy. Should recognize it from over here. It's a work integral. I think I mentioned that. It's just doing work in a circle. Okay, and that is going to be equal to a double integral of bx minus ay over dA. This is what Green's theorem is basically trying to say. And it can be written in another way. The curl and the k component of the curl, but this is going to be essentially a vector, and there's going to be an ij and a k. You're just going to take that third component and use that one right there. And then we're going to have the dA. Now, we didn't really take a look at the curl yet, so that'll be for the next part, but we just want to recognize that all these things mean the same thing, and they're all doing the same thing, and it's just going to be essentially this operation. Well, what we're trying to do here is essentially take shortcuts, because you could solve this side, which, you know, you'd have to plug in this stuff here and try to figure out that. And if it was a really weird, complicated shape, you could do that. But if it was a pretty simple one and you could sort of figure out the area really easily, then you can use this thing. And well, depending on which side you think would be easier to solve, that's the side that you're going to want to solve. Well, there's a neat little trick we could play with this integral. If we make bx minus ay equal 1, then isn't that just the integral of the area? So if we had a field that was, for example, negative y over 2 comma x over 2, then that would just be equal to 1. And then you could find the area by doing 1/2 the closed integral, and then you take negative y dx plus x dy. Okay, and well, this you have to solve by parameterizing. One more thing we can do in 2D is calculate the flux. So we can use Green's theorem to calculate the flux. And this is going to be, again, the circular integral from f dotted with the normal of dr. And these are, again, the same things that we've done here, but the major difference is that this is in a line just from one point to some other point, and this one is a closed one, a complete circle, or it doesn't have to be a circle, but the idea is it's closed. And this is going to be equal to the closed integral of negative b dx plus a dy. And you'll notice that those two things are the same because this is the same operation. We're calculating flux. But this time we have a shortcut. Because it's a closed integral, we have this shortcut. We could say that ax plus by dA, that would solve this integral nice and easily. And we have symmetry over here. We're missing something, so let's go ahead and throw in the shortcut. This is just another way to write this. It doesn't really, this is simply just notational purposes here. We can call this the div of f because that is the div of f. We'll get to that in just a second. But the curl is that, and this is the div, and so we can name them by we can name these things by their names. Well, what are these things, the curl and the div? Let's start with the curl. The curl is just going to be, it's a vector. All right, and this vector simply is very similar to torque. So the curl of f is really, really similar to torque. So I drew this thing. Let's say I had like a plate or something, and the plate was literally rotating, and it's rotating from the z-axis. Here's the z in this direction, right? So you can see that, this is x, y, and z, but essentially it's rotating on that z-axis, and yet it's in 2D, right? So if the curl is positive, then it's going to be a counterclockwise spin, and if the curl is negative, then it's going to be a clockwise spin. So that's cool. And this is going to be very kind of similar to doing a cross product. So we're going to cross this symbol with the gradient, or with the field. So we're going to take, we're essentially trying to combine the gradient with whatever field we have, but like this. We got an I, a J, and a K, and then we have these partials, because this simply equals the partials. So d over dy, d over dz. Alright, these are just partials. And then we would dot those or cross those with the field that we have. So let's say we want to calculate the curl in 3D. The 3D curl of f is going to have three components, x, y, z, and that's just going to be equal to cy minus bz, comma, az minus cx, comma, bx minus ay. And let's take a note that this portion right here, bx minus ay, is the same as this over here, bx minus ay. And that's why we can say that this is essentially the k component of the curl. So that's pretty cool. And if we were to do the 2D curl, then it would simply be x and y. Well, here you're going to get 0, here you're going to get 0, and here you get bx minus ay. So it really doesn't matter. You're always going to get bx minus ay here, either in 2D or in 3D. Well, let's take another look at this ending over here. If we could somehow make this equal to 0, then we're going to run into a conservative field. And a conservative field is going to be path independent, and the field that would work for this is going to be the gradient field. So the gradient field is a conservative field. That's the gradient field right there. So with that in mind, that means that the curl of the gradient field is equal to 0. And what that really means over here is it implies something like this, that if you're taking the line integral across the derivative field, you could actually make that equal to 0, because that's how you would solve this particular thing if this was a complete circle finished loop. Well, that was the curl. It was a little bit complicated, but the div is actually going to be really easy, because this is more of a scalar, and it's going to be really simple. So it's going to be kind of like taking the gradient and then dotting it with the f. It's not really the gradient, but it's more like the derivative field, and dotting that with that field. But this is essentially the sum of partials. And you'll see what I mean in just a second. It's going to be super easy. That means, quite literally, we're taking the d over dx, comma d over dy, comma d over dz, and then we're going to dot that with their field, which would be a, b, and c, right? And that's just going to turn out to be ax plus by plus cz. And so that's the sum of partials. Now, if the div is positive, the div essentially means, let's say you had a balloon here, and you're just going to fill the balloon with air. Then you're basically going to expand the balloon, and you'd get a positive div. So that means that it's expanding. And if you get a negative div, then you mean that it's collapsing, and air would be flowing out of this balloon. And one last thing about the div. This is crazy, but no matter what the dimension is, if you take the div of the curl, then that's just going to be equal to 0. What? Well, let's try to finish this off by going into 3D. We're going to calculate 3D circulation. And this is going to be Stokes' theorem. Stokes' theorem. And that'll basically say, we're going back to the red one. So that's f dotted with dr. That comes from over here. If it was in a circle, we could use that one, which is what we're using here. So we kind of have the next level of Green's theorem. Green's theorem only worked in 2D. Stokes' theorem takes that into 3D. So we'll set this equal to the curl of f dotted with the normalized normal, and then the ds. Now the ds comes from here, and well, let's just take a look at this normalized normal here and ask yourselves, where is it? Well, that's what this k thing is representing. In 2D, the n is just going to be the k component of 1. So we're just looking for that k component. But in this particular case, this isn't in 2D, so now we actually need the full normal, so we're going to get a more complicated thing. But it's still a shortcut, so it should work out pretty well. And we can also find 3D flux, and that would be the divergence theorem. And so that would simply be a double integral, and we have the field dotted with the normalized normal, and then there's the ds again up there, and that's just going to be equal to a triple integral of the div of f over dv. And we can see where that comes from over here, where we'd have, instead of the a, because it's in 2D, it would be a v because it's in the 3D. So hopefully this stuff was relatively helpful, and it's crazy stuff, man.